All right, again, welcome everyone. We are very happy to welcome Brian Swingle from now Brandeis University. And he will tell us about what the title says. So take it away.
All right, great. Thank you all for the invitation. Thanks for coming out. And yeah, today I'll speak to you about quantum gravity in the lab. I'll, of course, define what I mean by that a little bit later on and give you some different examples of early work in this area. This is a new field. I hope it's at least somewhat related to what the people that attend this seminar think about. Really, we're kind of trying to bridge the gap between the kinds of systems we can analyze using holography on the gravitational side and the kinds of systems that we can realize in the lab. We want to ultimately bring these two sides together to bridge that gap and to be able to describe systems we can construct in our labs using gravity, and maybe also learn about gravity using those same systems. So that's the broad outline. And yeah, I don't know what your standard protocol is, but I'm fine if you want to interrupt me at any time to ask questions. And yeah, I'll also just acknowledge the funders, IT from Qubit, Department of Energy, Air Force, and National Science Foundation that have supported various aspects of this research. So let's get started. So what's this about? I want to pitch it as holography meets quantum simulation. That's what I'll mean by quantum gravity in the lab in more detail later. This is a new field, it's an emerging field. And so what I want to do is, rather than try to go into depth on any one topic, I'll give you 3 brief stories that illustrate different aspects of this field and give you a sense of what people are up to and what are the questions that we're trying to tackle. And if you're interested, what you could get involved with. I'll talk about, first of all, quantum gravity as a source of surprising phenomena. So this is sort of like using quantum gravity to understand otherwise mysterious experiments with quantum many-body systems. So I think this is very much in the spirit of what many of you think about. Then I'll talk about efficient algorithms to simulate quantum gravity models, which means to simulate many-body models that have holographic duals of some form or another. As you might imagine, figuring out how to simulate the large N non-abelian gauge theory is not a trivial task. And we sort of know in principle how to do that, but it's not known how to do it in a very efficient and cost-effective way. So I'll talk about a version of that story with a very simple model, the SYK model. And then, although everything we're talking about is in the context of holography, quantum gravity in the lab can, of course, mean something more general than that. And one thing you might want to do is access cosmology, cosmological observables in some form or another. And so I'll talk about one idea that we've been working on in the last year or two called microstate cosmology, which is trying to get at cosmology, braneworld cosmology specifically, within ADS-CFT. So that's the plan. And I'm going to start by coming back to this question, what is quantum gravity in the lab? And I'll start with the honest statement that we're not sure what we want to mean by this phrase. It's more aspirational or inspirational than a complete definition. I mean, certainly one thing that we hope to one day do is experimentally probe what you might call the naturally occurring gravitational field, the field that keeps us all on the Earth, the field that is relevant in cosmology, etc. But that's hard. I mean, we can probe gravity easily enough these days, but probing quantum effects of gravity is extremely difficult. Maybe the best chance we have in the near term is some kind of cosmological observable where we see holdover from primordial gravitational fluctuations, for example. But seeing direct evidence of gravitons is challenging. And so I'd like to argue that we'd also want to include in our notion of quantum gravity in the lab experiments with engineered quantum systems that exhibit in a clean and well-defined way some kind of emergent gravitational description. So in other words, if you could, using a quantum computer or some sufficiently controlled quantum many-body system, effectively engineer or simulate a system that behaves like super Yang mills in the large N strong coupling limit, surely we'd also want to call that quantum gravity in the lab. And the vague kind of guiding principle is, I want to use this phrase anytime we're talking about a system where there's some kind of simple by some metric description of the system which involves space-time geometry, some kind of fluctuating space-time geometry. Of course, we have not seen definitive evidence for quantumness or gravity in our own universe, but it's very likely the case that we're in this class. But as emphasized above, this can also be true for tabletop experiments. And that's kind of what I want to focus on in this talk. And we may want other conditions, like we may want black holes to be present if we're especially interested in the quantum physics of black holes. But I'll leave that to your imagination for now. And so here I just want to pause and kind of dwell on this rather remarkable fact for a few minutes. The fact that by combining holographic duality and quantum simulation, we really can do an experimental simulation of quantum gravity in some kind of universe. This is not really, I would say this idea kind of came to a slow realization to many people. It's not, itself a super crazy combination of these two things, but these two things by themselves, holographic duality and universal quantum computation, are highly non-trivial things. And the combination of the two of them enables us in principle to simulate certain kinds of quantum gravitational phenomena in the lab. And, I want to emphasize you'll be doing this not just to, say, verify some aspect of holographic duality that you already know is true, but actually to probe a holographic theory in a new regime that you can't access easily using your analytic tools. So we can really hope to actually learn about quantum gravity, at least some models of quantum gravity, using experiments. And that to me is very exciting. So this is I would say, a non-trivial combination of these two big ideas. It's something that we're working towards. We're not there yet, but even just the process of asking how you might in principle do this, what you'd want to measure if you could, etc., is an interesting and profitable endeavor. And, we may actually not be that far away from simple versions of this kind of experiment in the lab in the relatively near future. Okay. So for this talk, I'm going to stick to a relatively narrow sense of quantum gravity in the lab, where it necessarily involves holography. So the boundary, the CFT, whatever, is the thing that we construct in the lab, and the bulk, the emergent thing, is the quantum gravity. I'll emphasize again, this doesn't have to be the only meaning of quantum gravity in the lab, but it's what I'll mean here. And in this definition, the gravity that holds us down is not directly related to quantum gravity in the lab. So of course, we hope that the lessons that we learn can be more generally applicable, but we're specifically talking about laboratory systems where the naturally occurring gravitational field is irrelevant, and we're engineering these quantum many-body systems to exhibit a dual description which has some gravitational component. So in this narrow sense, then there are investigations that don't qualify. So for example, analog simulations of Hawking radiation. So if you think about some acoustic system where you force a flow faster than the speed of sound, you can have an effective horizon and effective Hawking radiation. That's interesting, but it's not what I'm going to talk about here. There are various reasons why it's not, what's the right word? Well, there's various things it doesn't capture very well, and like the quantum physics of black holes as quantum objects themselves, rather than just the physics of quantum fields on top of black hole background. So if we really want to study that quantum physics of black holes themselves, then maybe we need something more. So again, this is interesting, but just not what I'm going to talk about here. I'm going to stick to this holographic sense of quantum gravity in the lab.
Brian?
Yeah.
Hey.
Hey, Blaise, how are you?
Good, thanks. Can I interrupt with a question here?
Please, please.
So I think it might become clearer as you move along, but I'll just ask it now. So I assume you'll depart from the boundary system.
Depart? What do you mean by depart?
Your starting point will be
That's right.
the boundary system,
the thing that you
can have in the lab.
Yeah.
But how can you guarantee that this is something that might have a holographic dual? Or because I guess one route that people might think about these days, and that you probably thought about, is design some quantum system that models SYK, or that is well modeled by SYK. And then you can bootstrap that to argue that this is dual to near radius 2, etc.
Yes.
But will you tell us about other examples?
I I won't tell you about other, I mean, I will talk about SYK, and I won't talk about other models that have, like a new model that has a quantum gravity description. I'll talk instead about if you had a model that had a quantum gravity description, what might you learn from it, or what surprising things could you do with it? I'll talk about how you might tell if there is one. So that's, of course, a question we'd like to answer. It's hard to know the space of quantum field theories, which of them are holographic and which of them are not. That's a difficult strong coupling question. So that's a question we'd like to actually answer using this technology when it one day exists.
Okay, thanks.
Right. Yeah. Yeah, so the first thing I want to speak about is quantum gravity as a source of surprising phenomena. So this is going to be about an experiment that you could just hand a blueprint for this experiment to your experimentalist friend and ask them to do it. And there's a surprising outcome. And that outcome is at least inspired by quantum gravity reasoning, inspired by wormholes, in fact. And in some particular setting or limit or configuration is actually directly related to some sort of simple quantum gravity phenomenon. This is work that I did with a bunch of people: Adam Brown, Grant Ribian, Stefan Leichenauer, Henry Lin, Sepra Nizami, Grant Sultan, Leonard Susskind, and Michael Walter. This was, the first paper appeared in 2019. We had just a second part that came out a few days ago, I guess, or a week ago, in a coordination with the group of Schuster et al. This is Norm Yao's group at Berkeley. And this is really about teleportation and about wormholes. That's the basic setup. So here's an experiment that you could hand to your experimentalist colleague. Let's understand the setup. So let's look at the left picture here, the state transfer picture. So I start with a thermofield double state. That's this triangle at the bottom, labeled TFD. So this is an entangled state of two systems, such that if I trace out the left side or the right side, the other side looks thermal. Okay, so it's like a minimal heat bath that produces a thermal state. And I divide the left side L and the right side R into two subunits, A left and B left, and correspondingly B right and A right. You can think of A left as being small and B left as being like the rest, but it's not super crucial. And I want to do the following experimental protocol. I have a Hamiltonian. First thing I'm going to do is I'm going to evolve backwards in time with the Hamiltonian on the left. That's what this first block does with the downward green arrow. Then I take this qubit, say, in A left, suppose it's just one qubit. I throw it away, so I just take it out of the circuit. It doesn't do anything after it. And I inject a new quantum state, a new qubit in some state psi n into that hole in the system. And then I evolve system forward in time for an amount of time equal to the backwards part, but now forward. Now I couple the two sides. I couple left and right on the B subsystem with a unitary coupling, which has a strength G, and the interaction is called V here. You can see it. Let me move the picture box. You can see it here. This sum over carrier qubits is the sum over qubits in B. It's the poly Z on the left, the poly Z on the right, and there's some normalization. So each particular interaction between pairs of qubits on the left and the right is weak. It's 1 over n suppressed, where n is the number of qubits. But I'm adding it up over all the carrier qubits in B. Okay, so it's just a weak phase for each, in the Z basis for each pair of qubits, but I add up over all the qubits. And now I go on the right side and I evolve forward in time for the same amount of time as I evolved on the left. And if you do all this procedure, and if, for example, this thermofield double, suppose you have a spin system, suppose it's at high temperature compared to the lattice scale. So it's a nearly maximally mixed state. So this is just Bell pairs. And I suppose I evolve for a very long time and I tune this coupling G just right. What comes out on this psi out is exactly psi n up to a very simple known unitary transformation. So in other words, it in essence transports the information from the left to the right somehow through this complicated circuit. Okay, that's the description of the setup. It may not be clear to you why it does that transformation. It may not be surprising. It may be surprising. I don't know. I would say you should be surprised by this, because if this only works when this left Hamiltonian, right Hamiltonian are chaotic scrambling Hamiltonians. So what's really happening is you are preparing some very funny initial state, which is the thermal field double, but evolved backwards in time. Then you're throwing in some information, you're scrambling it up, you're weakly coupling the two sides, and you're evolving somewhere on the right, and the information comes out again magically from this scrambling procedure, essentially undisturbed. The unitary transformation for a single qubit is just applying sigma y to it. So it's trivial to recover the initial information from the output information in this case. There's also an operator transfer. This is a state transfer because I'm putting a state here, but you could also imagine moving an operator, which is acting on a left to acting on a right. But this is the basic setup. And so your experimentalist friend could do this. They could carry out the experiment, and they'd find that the input and the output are correlated in this very nice and simple way, despite the fact that you had all this complicated scrambling structure in the intermediate. So what's going on? Well, the idea is this protocol is inspired by the idea of traversal wormholes in gravity. How does that work? So let's draw the gravitational dual of the picture we started with, the left-right system in an entangled thermal field double state. So here's the space-time geometry, which represents that entangled state. Here's the L CFT on the asymptotic left boundary, the R CFT on the asymptotic right boundary. And now we kind of see the way that these different pieces of our circuit correspond to inserting of a message. We start, say, at the time 0 slice here. Then we go backwards in time on the left. We insert our message. The message comes in. And if we don't do anything, then of course the message just falls in and it hits the singularity eventually, and it never comes out on the right side. So obviously, if we don't couple left and the right, there's no way the information can get through. That's just basic microcausality. But if we do couple them, then there's at least a chance the information can get through. And what these authors showed was that in the context of ADS-CFT, if you choose the coupling in just the right way, it can inject some negative energy, which you can think of as essentially like on the right, a shock wave of sorts that has a negative Shapiro time advance instead of a time delay, which kind of takes the message that's falling in, it kicks it out, and then it comes out and is received on the right boundary at some time in the far future. So now you see the correspondence. I start from thermal field double, I go backwards in time, insert my message. Then when I get back to time 0, I couple the two sides. That's injecting this negative energy, which then brings the message back out, and then I receive it on the right boundary at some time in the future. Okay. But this is a very particular holographic setup. I'm not claiming that every version of this experiment that you can do is realizing this physics. In fact, this only corresponds to a certain particular situation where the temperature is low. But it's at least inspirational because it turns out that, first of all, if you wanted to know if you had this nice bulk, you could, in principle, do this kind of experiment and see if the information that you're getting out conforms to this picture, if you can actually transmit information. But there's also new phenomena. So for example, as I described here, if you go to a very high temperature, and you go to a very long time, this picture is no longer the right one, but actually you still can transmit one bit of information reliably. And that works for any quantum many-body system. So the picture I'm advocating for here is we have this holographic protocol, if you like, a teleportation protocol, traversal wormhole protocol. We can extract the blueprint for that protocol and then give it to the experimentalist. And in some limit of that experiment, you can recover this holographic picture if your system is a holographic one. But the protocol makes sense more generally and actually gives you some surprising phenomena that you would not have expected otherwise. Like if you just had someone do this, I don't think they would expect that the output would be some simple function of the input. But once you know about quantum gravity and you have this picture in your mind, then it's less surprising. And what we want to do, one thing we want to do is have a purely boundary quantum information way of thinking about what's going on in this kind of protocol and under what conditions you might have a gravitational description and what conditions you have successful information transfer. And to do that, we introduced in our paper a notion that we called size winding. The paper is called Teleportation by Size. And we introduce this notion of size winding, which is defined as follows. So let's start with the thermal field double again. This little V shape here is bell pairs. We can always make the thermal field double by starting with bell pairs and applying the square root of the density matrix to one half of it, say the right half. You can just do a little algebra and check yourself that that's the thermal field double state. And if we apply an operator O left with the transpose on the left system, because it can pass through these bell pairs up to a transpose, you can check that that's equivalent to acting with the same operator on the right and then the square root of density matrix. Right? So in other words, operator on the left can be brought over to the right, but it occurs after the application, or well, if you're reading from the top down, you will apply, I mean, from the bottom up, you would apply right operator first and then the square root of rho. Now, you want to compare that for this purpose of teleportation to what would happen if we apply the operator to the right side. In that case, we're applying square root of rho first and then the right operator. And so what you see is there's a difference in ordering. On the left, we're getting the square root of the thermal state times O right on the bell pairs. And on the right, we're getting the right operator times the square root of the thermal state. So it's suggesting that this square root of thermal state times right operator is the thing to think about. We want to understand how these two things commute or fail to commute. And so the idea is, let's look at this operator, square root of rho times O. This is generically non-Hermitian, even when O is Hermitian. And so we can imagine expanding this operator on a polystring basis. So again, I have qubits in mind. We can expand this operator in a complete basis of operators, which is just a list of all possible polystrings. So for example, if I had 3 qubits, one polystring is identity, identity, identity. One of them is X, identity, identity, etc. So there's 4 to the n possibilities for n qubits. And this forms a complete basis of the operator space. And I can expand my operator in terms of this complete basis. And I'll define an object GL, which is just the sum over the coefficients squared, the amplitude squared, without absolute value, so just the square. The sum over all those coefficients with Pauli strings of a fixed weight L. Here, weight means the number of non-identity elements in the string. So the L equals 1 case would include X identity, identity, Y identity, identity, Z identity, identity, etc. And the idea is we introduce something called perfect size winding ansatz, which says, suppose this operator, when expanded in the Pauli basis, has the form of Pauli times a real number times a phase. And that phase depends only on the weight of the Pauli. It's normalized by n, and there's some free parameter alpha here. So this is saying the only complex part of this amplitude is just in this overall phase. And it's a perfectly linear phase with the weight of the string. So this is not the most general possible ansatz, but it's a restriction on the possible things you can have. But we're saying, suppose you have this ansatz. Well, now we can figure out how this thing acts on the thermal field double. If it acts from the left, then what you get is square root of rho O. That's just the Pauli string itself. So we have e to the I weight over n times these coefficients, sum over all Pauli strings. If it acts from the right, you'd have the same thing, except now you just need to take the dagger, right? Square root of rho times O is the dagger of O times square root of rho. So we just dagger that. Because the complexness only comes in the phase, all we need to do is change the phase to minus itself. And so you see these two things, these two options, have roughly the same structure, except they have equal and opposite phases that are winding in clockwise and counterclockwise directions. And now the magic of this left-right coupling comes in. What does this coupling do? Well, you work out the algebra, and it turns out what it does is essentially apply a weight-dependent phase to the Pauli string. Roughly speaking, what's happening is this is counting the number of X's and Y's in your string, and they get a phase, and the Z's and identities don't. So it's proportional to the weight. And So when you apply this operator to a state, it just gives you a phase, which depends on the weight of the Pauli string, times some number that's related to the strength of the coupling. And so now you see, if I applied this particular transformation to one of these states, and I chose alpha and G to be correlated in the right way, then I could flip the clockwise phase to the counterclockwise phase, which would effectively be moving my operator from the left to the right or vice versa. Okay, now what's going on here? We can try to translate all this into the holographic picture, and what it turns out this all has to do is this phase is really just the wave function of an infalling particle. It's related to the momentum and the position in this convenient null basis, this light cone-like basis, where we have sort of messages following light lines. And so this size winding is like a statement that what you have is you have a wave function, which is some kind of plane wave, and then you kick it a little bit to a different plane wave state, which amounts to just changing its position, which is moving it out like this, and then it comes out the other side. So in other words, this size winding is a sort of purely quantum information, quantum mechanical way of expressing the fact that you have these wave functions and this motion in this bulk geometry, but purely in terms of Pauli strings and this operator expansion, something you can measure using your quantum computer without needing to know anything about a putative bulk dual. And so our proposal in this paper is that size winding is the boundary manifestation of ability to teleport through a wormhole. And you can also check, as we showed in the second paper in detail, that both SYK and also JT gravity have this size winding in them. So it seems to explain what's happening if you did the protocol in that case. And so in this situation where we have a setup that's really holographic, we have a really holographic model, this size winding can explain the observed signal in sort of quantum information terms. So it's a surprising phenomenon that you would see if you did the experiment, which we can't understand in terms of this winding of the phase, but which would have in principle, in the right situation, this very nice holographic description. Now, just to emphasize, there's different regimes here. What I talked about most for the size winding point of view was what we call perfect size winding, which is this panel D here. This only occurs in certain situations. For example, in the SYK model, you would need it to be low temperature. It depends on the sign of G. I think that's pretty clear because we need G to be correlated with the sign of alpha in order to change the phase. You can translate a lot of information this way, it turns out. There's various features. So this is not generic, but it could be, if you like, a fingerprint or some part of a package of evidence that convinces you that your system is holographic. On the other hand, you could look, for example, at very late time at high temperature. That's what's shown in panel A. And what you find there is that you can reliably transmit only one qubit, but you can do it for any system, right? It doesn't have anything to do with holography directly. Any chaotic system will do it. And the bulk interpretation of this is something more complicated. You know, it's like superpositions of geometries or something like that. It's a more elaborate story. Precisely because it doesn't work for, because it works for any system that's chaotic, it can't have a simple explanation that relies just on gravity in some semi-classical situation. And I won't go through these other cases, but there's just a whole regime of intermediate behaviors where you can get various kinds of things. And all these different behaviors are inspired by the gravitational setup. You only literally have a holographic interpretation in certain regimes, but this is really like a set of experiments that you could do that are surprising to start with, and which could help you, say, figure out if a system that you don't know the physics of is in fact holographic or not. Okay, so I'll pause if there's any questions. If not, we'll go on to the next topic. Okay. So that's a general experiment that you could do in whatever your system is. And if you look in our paper, we have simulations of.
Sorry, but Brian, before you go on,
Please.
This is really my own ignorance of this type of physics. But can you say again, why is this size winding?
Yeah, sorry, maybe I didn't even say this. So this weight is sometimes called operator size. So it's like how many non-identity elements you have in your operator string. So this is a winding of the phase that depends only on the size of the operator, which is why we call it size winding. And maybe the backstory, which I don't have time to dwell on too much, but is that this operator size plays a crucial role in, for example, quantum chaos. So you can think about the growth of OTOCs as growth of operator size. Your Heisenberg operator, which you conjugate, starts simple. It's just one operator, say on a single qubit. But then as you evolve in time, it gets more and more complicated. And what you find is that if you looked at these coefficients, these expansion coefficients, they would expand to have support on more and more complicated polystrings. And so the average size of your operator would grow. And so then there's the relationships between operator size and momentum in the bulk. There's been proposals for how to write operator size in terms of like near horizon generators in JT gravity, et cetera. So there's like a rich literature there relating operator size in some form to bulk quantities. But here we're just using it in the sense that this phase depends on the operator size or weight and has this nice winding.
Question?
Yes, please.
So can you get rid of this restriction of the ansatz, like transport more general operators? What it would take?
Yeah, so I don't think we have the full picture yet, but so one situation would be where you're at infinite temperature, in which case this square root of rho is just identity and it's just Bell pairs. And now in this case, if O is Hermitian, then this expansion coefficients must be real, so there can be no size winding. So infinite temperature, there's never any size winding. Nevertheless, it turns out you can transmit one bit with perfect fidelity in the state transfer version of it, provided you tune G correctly. And this is essentially because, well, what's the simplest way to see it? Essentially what this ends up doing, this combination of the time evolution on the left and the right with this particular unitary produces a many-body operator that applies a phase of e to the ig to the Bell pair state and does nothing to any other state. So it's a very particular quantum gate that just changes the phase of the thermofield double and does nothing to any other state. And you can then show that if you have this kind of quantum gate, it will exactly transmit one bit in this way. So it's not super intuitive, I would say. It's a funny regime where you don't have anything to do with size winding because these coefficients are all real. But nevertheless, you can transmit one bit perfectly. And so that's what this different regimes is supposed to indicate, that there's different limits where you have, say, the ability to transmit one bit, but for any quantum system versus the holographic setting where you can transmit many bits, but only if you have this nice dual description or in the operator language, this perfect size winding. So there's really a landscape of possibilities, and rather different regimes of that landscape have a nice interpretation in terms of some gravity description is not clear to me. Like, I think this is an open question.
Mm-hmm.
Okay.
And Brian, what does damped mean?
Damped. Oh, here. Oh, it means that the amplitude is decaying. The amplitude of the phase winding is decaying.
Because it also looks like it's decaying on the right side for the perfect size winding.
Yeah, it's probably just not a super. I mean, it's decaying. Let's say it's strongly decaying versus weakly decaying. It's not a super sharp distinction. But essentially you see here, you need to change the phase over like many winds essentially, because This is one over n suppressed. So you need it to extend over a large range of operator weights. And if it's not doing that, then it's harder to send the information.
Thanks.
Yep. All right. Yeah. So going back now, if suppose we wanted to, so that's like something, what I just told you was something surprising you could do with your quantum gravity inspired algorithm. And on the flip side, maybe it's something you could use to try to tell whether a system in your lab has a nice gravitational description or not. Suppose you wanted to actually build such a thing. I mean, we don't think a spin chain has this property, but maybe some more complicated model does. The simplest possible model that probably has something like a gravity description is the SYK model, as far as we know. So suppose you wanted to simulate the SYK model in your quantum computer. Suppose you wanted to engineer your system to behave like SYK. How would you do that? Well, there are ideas, and what I will tell you now is that there's an interesting twist in the model, a variant of it, where you can have a much more efficient simulation. And it's non-trivial to figure out, how to do these efficient algorithms. So this is kind of an example where you can, by changing the physics in an interesting way, do a more efficient simulation. So this is work with Shenglong, Yuan, and Lenny. And let's review SYK to start. So probably this is something you've all seen before. I imagine it's hard to get away from it. You have Majorana fermions, real fermions. You have n of them. And the Hamiltonian for the SYK-Q model is just we sum over all Q-body fermion interactions with some Gaussian random couplings and start normalization. This model has been studied to death, and we're going to study it to death some more, but we're going to study it to death a version of it. The idea is, what if you want to simulate SYK? Well, the early work, Garcia Alvarez and company, showed that you can do that by toroidalizing the quantum circuit. This means just breaking it up into little pieces and using basically Taylor series to write down an approximation of the time evolution operator. So they took the first step to show that this was possible, but it was quite expensive. So if you want to simulate an SYK with n fermions to precision epsilon for time t, you need a number of quantum gates which goes like n to the 10 times time squared divided by the precision. And that's extremely expensive. Among other things, it's not even linear in time, which is kind of weird. So if you want to simulate it for 100 seconds, you need 100 squared gates. You would normally think that you would have a linear in time simulation algorithm. Now, some people, then Babish, Berry, and Nevin, applied more modern simulation technology from quantum computing literature. They goes by the name of asymmetric qubitization. I won't explain what it is. Don't worry, it's just a thing invented by Lo and Chuang. And what they showed was that you can get the simulation cost down to scaling like n to the 7/2 and linearly in time, plus some subleading things we won't worry about. So this is good. The linear in time is about as good as you can hope. And the scaling with n is expensive, but much better than n to the 10. And the essential reason why this n to the 7/2 is appearing is because, first of all, fermions are non-local in terms of qubits. So you need to write them in terms of like Jordan-Wigner strings or some qubit expansion which captures the fermion anti-commutation relations. And secondly, because what matters for quantum simulations, at least the ways we know how to do it right now, is the L1 norm of the Hamiltonian. So you need to take all these terms, these j's, and compute the L1 norm of this thing as a vector. So you add up linearly the absolute values of all the j's. But this normalization is chosen so that the L2 norm of this Hamiltonian is nice. That's kind of what we want in physics. That's how you get standard large N expansion. So there's this funny mismatch between what you can prove in your quantum simulation algorithm and what's natural from a physical point of view. And that mismatch is why this scales super linearly with n. Ideally, if you had a system with n degrees of freedom, you want it to evolve for time t, that should cost the number of gates which is proportional to the number of degrees of freedom and the time. But what we're seeing here is a cost that's more expensive than that for these reasons. I won't talk about this at all. There may also be ways to simulate this using analog devices. like cold atoms or graphene flakes. It's beautiful work, but I won't dwell on that here. So we wanted to improve this, at least I wanted to improve this. That was one of the reasons for what we're about to talk about. And what we said was, okay, if you were doing it a spin chain or something like that, then you actually would have a simulation cost that scales with n, not with n to some power. So could we mimic that in the case of SYK? And the idea was to define what we call a sparse SYK model. The way it works is like this. You go through interaction by interaction. Here I'm showing you the q equals 4 case. And you just start deleting randomly different of these interaction terms. So you introduce a new parameter, x, a, b, c, d, which can either be 0 or 1. And the probability that x is 1 is p. So p is like the pruning probability. And so we go through term by term, we just delete them randomly. And then if the probability p is close to 1, then most of the terms are kept. If it's close to 0, then we start deleting many of the terms. And you can show that just by counting that the number of terms you expect after this procedure is p times n choose 4, which we define to be kn. So this defines the parameter k. And so the idea is the non-sparse limit, the fully connected limit, is where you take n to infinity with k going like n cubed. That means p is just, say, a half or a third or 1, whatever. So you're deleting some terms, but you're keeping most of them. You still have roughly n to the 4 terms. But there's now a new limit where we take k to scale more slowly with n, or even to be fixed as you take n to infinity. And in this limit, the number of terms now scales with n rather than n to the 4. So it's much more like a spin chain, something where if you have a spin chain, the number of terms in the Hamiltonian is proportional to the number of sites. So this is a new model. It's a new class of models, which has the same kind of structure of these 4-body interactions or q-body interactions, but now the number of such interaction terms is more limited. We have to rescale the couplings according to this rule in order to have something which looks like the same kind of normalization, the same extensivity property for the Hamiltonian as we had at SYK. So this parameter p appears there. And in particular, if we take p to scale like 1 over n cubed, then we're deleting almost all the terms, but now the number of terms that remain will be proportional to n. And this k will be a constant in a large n limit. And okay, from the point of view of quantum simulation, what's the virtue of this? Well, here I show the result for fully connected SYK, it's n to the 7 halves. We can now get this down to something which depends on k times n squared log n t. And more of this works for any q. In their paper, Babish, Barry, and Nevin only studied q equals 4. If you did the analog of their calculation for general q, it would be scale like n to the q plus 3 over 2, which is quite expensive when q is large. But our result does not depend on q. So no matter how big q is, you can still simulate the sparse model with this cost. And going from n to the 7 halves to n squared, if you think of k as order 1, that's a pretty dramatic drop. If n is, say, 100, this is a reduction by a factor of 1,000 gates per time step to evolve the system forward in time. So instead of needing 10 million gates per time step, you might need 100,000 or even fewer, okay, which is a rather dramatic speed up. In fact, there's another way to do it, a different way of simulating using what are called product formulas. Think of these as like fancy versions of trotterization. And in that case, we can get this cost down all the way to almost linear in n, which is the best you can do. And the reason why it's still n squared here is essentially because fermions are still non-local in terms of spins. So you still have to do some complicated fermion to spin mapping. And that is important actually for getting the physics. But you could possibly improve this a little bit more. But the basic point is this sparsity, this addition of sparsity really helps the simulation. It goes a lot faster. But the question we need to answer is whether this sparse model still has gravity physics in it. I won't go through the details of this analysis. We can't analyze the model as robustly as we could for the fully connected SYK, but we still have a set of evidence that we think indicates that you have gravity present. I'll go through the argument very quickly here. One way to approach this is to do a path integral kind of approach, like for normal SYK. You have a Lagrangian Lagrange multipliers, G, which is like the 2-point function, except now it depends on the fermion index because the fermions are distinct from each other. It's no longer a mean field. And you just have a replicated partition function, which you write in a standard way. What you can show with a certain kind of nice condition on the structure of interactions, that they have a regularity condition, that they form what's called a hypergraph. I won't really explain that, but just think of it as a regularity condition. You can show that there's equations of motion of that action have solutions, saddle point solutions, which are identical to the fully connected case. So the saddle points are the same, at least a set of them. And then you can ask about fluctuations on top of those saddle points because it's no longer a large N controlled mean field. Now you have fluctuations on every site. And we analyze those fluctuations. This is just to show you there's some equations, complicated looking equations. You can look at the details in our paper for the details. The crucial point is that the fluctuations, the quadratic fluctuations, have a certain structure. You get a term which is diagonal in site indices times the standard kernel you'd have for the fully connected model. So this is like the kernel you get in full SYK, the quadratic fluctuation kernel. And then you have another piece, which is diagonal in the times. So it's just identity as far as the SYK part is concerned, but it's non-diagonal in space. And it's some kind of effective hopping matrix or adjacency matrix on a graph. That's this MAB. And the spectrum of quadratic fluctuations is really coming from the combination of these two terms, the SYK part and the fully connected limit and this graph structure. And what happens is this graph, if you choose it in a nice way to be an expander graph, then this matrix M has one eigenvalue, or one eigenvector of eigenvalue 1. That uniform mode reproduces the physics of the fully connected SYK model. So that's your gravity mode in a low temperature limit. And all the other modes are gapped. So at the level of quadratic fluctuations, they're gap fluctuations, and at low temperature, they don't contribute to the heat capacity. Here's a picture of the spectrum. This red line is what becomes the gravity mode in the fully connected case, and we still have a mode there. This blue part is the rest of the spectrum of M, and the spectrum of this K inverse thing extends above the red line and below this pinky bit down here. So you see there's no other overlap between the blue and the red, and that means there's only one soft mode. That one soft mode is the same soft mode as you had in the fully connected model. It's at low temperature, it's the Schwarzian mode. Okay. So altogether, this pattern analysis gives us pretty strong evidence at the level of the quadratic fluctuations and the saddle points that you still have the same kind of low energy mode structure you had in the fully connected model. There are other modes now, but they're all gapped. We can also do numerics, actually bigger numerics than you could do otherwise. And in those numerics, we can study in finite size. So here on the left, I'm showing you the entropy as a function of temperature. I'm comparing the mean field answer, so this is just solving the Schwinger-Dyson equation, that's the black line there, to different numbers of fermions and different values of K. In particular, it's hard to see, there's like a red line and a blue line that line on top of each other right here. That's n equals 52 with different values of K. So you can see that K barely changes the answer at all, even if K is 4 or 8. And then by contrast, there's also a green line, which is n equals 40 fermions, and that's a little bit different. So in other words, blue and red are almost the same, so there's very little finite K effect, but there's still some significant finite N effect. This is for Q equals 8, which is actually will be extremely hard to do with 52 fermions. The full model has about 750 million terms in the Hamiltonian, whereas the sparse model has about 208 or 416. So we're vastly, vastly, vastly reducing the number of terms. But nevertheless, we're pretty close to the mean field. And if we include the 1/n correction, which seems important, that's what's shown in this inset here. The blue is the data, the black is the mean field, and the dashed line is what you expect from the leading 1/n correction from your analytics. And you see that it's just perfect. The slope is perfectly what you expect it to be as a function of temperature, including the prefactor. This is coming from a one-loop determinant around the saddle point action. So we have very strong evidence from numerics and from our analytics that indeed you have this gravitational mode at low temperature. The physics is reasonably simple, I think. It's just that you have gravity coming from a certain pattern of symmetry breaking, a certain pattern of discrete and of explicit and spontaneous symmetry breaking, and that pattern continues to persist in the sparse model, provided you have enough connectivity. And so the conclusion is we have this sort of interesting deformation of the model, this sparse deformation, which retains the interesting physics, but also makes the simulation a lot easier. So this is much closer to realization in a quantum computer than the fully connected model, but it seems like we could still access interesting gravitational physics using that kind of simulation. In particular, we could still do that teleportation experiment I described in part 1 and have it work with high fidelity in a low temperature regime. Okay, I'll pause here again if there's any questions. If not, I'll go on to the third and final topic briefly.
I have.
Please.
So in the quantum simulation, I got a bit lost. How do you combine the noise implicit in the J's with the quantum simulation? Do you update the quantum circuit at each step, or you run it and then average over the J's afterwards?
That's right. Yeah, it's the second one. So we need to keep the J's fixed on a single run. So yeah, you would actually just fix the J's, which means fix some circuit elements in your circuit and repeatedly apply them to evolve in time. And then once you've done your data collection for that run, then you could do a different set of J's. And so those J's are something you generate, on your classical machine. You just ask it to produce some Gaussian random numbers, and then you plug those into your quantum circuit generator, and that produces the circuit. For many purposes, it's actually reasonably self-averaging, so you only need to do, a few runs. Like I think this picture here is only averaged over, I forget, maybe as few as 10 different runs. So it actually converges quite well as far as entropy is concerned. But for certain finer grained issues, you would need definitely to average over the different runs. Other questions?
To make sure I've understood, if I recap, you considered a model where you pruned some of the terms.
Yes.
And essentially what you're showing is that this pruned model still retains the essential same physics as the original model, with like the gazillion of terms that no one can put on a computer or solve.
That's right. Yeah.
Okay.
Yeah, and in fact, so not only does this make the simulation easier, it lets you access things you could not access before. So for example, large Q models, like there's this double scaling limit where you take Q to scale with n in a certain way, like square root of n. That's actually something we couldn't do on a quantum computer or even classical computer really at large n because it's super polynomial resource. But with the sparse model, you can actually do it. So you could, in principle, quantum simulate these funny large Q limit models in a polynomial amount of time with n and actually study their physics if you wanted to do that.
Do you have enough analytical control to show that the Schwarzschild comes out, for instance, at low temperatures, or is it harder?
At the quadratic level, we can show that it's the same action. So we can get at that level. We don't have control over the higher fluctuations. There is like a 1 over k expansion, or really a 1 over kq expansion. And if you go to high orders, then there are corrections. What we suspect is that probably in some sense they're irrelevant at low temperature, so that they flow away to 0. But we don't know that for sure. At high temperature, you can just like directly compute 1 over k correction and find that it is some small correction. And we don't know why it's small, but it just seems empirically to be a pretty small effect. So it changes the heat capacity by like 1% or something when k is 4. And so it just doesn't seem to have a dramatic effect. anywhere. But it's definitely possible that, you know, there's the coefficient of the Schwarzian or something could be modified by some 1/k effect. We think that the Schwarzian itself is there, but we don't know, you know, the details of the coefficients perhaps, and we don't know the higher order relevant corrections to it. Those could depend on K.
I have a question. Yeah. Yeah. Hello.
Hello.
Hello. So to find, for example, a thermophile double ground state in this sparse, is it easier, or people have used sometimes variational quantum eigensolvers to find thermophile ground states?
Is it easy? Yeah, in the quantum simulation sense, I would guess it's probably easier, just because it's easier to evaluate the energy.
Mm-hmm.
In a variational sense, for example, like it takes many fewer gates and there are many fewer terms. There are also other ways of trying to make the thermophile double by coupling the two sides in some way, for example. We did not study that, but I think it would also work and would be, again, easier. So I think it probably is easier.
Okay, thank you.
Okay. There's also, now I think about, there's this so-called, you can effectively evolve an imaginary time using some unitary gates that approximate the effect of the Euclidean evolution, and that should also be easier, I would think, in this setting. So it seems easier, but we didn't analyze it carefully. Okay, so in the last couple of minutes, let me just briefly highlight one other thing we can think about. So far I talked about, very much in the context of ADS-CFT, how you could simulate ADS-CFT essentially, the kind of models you might want to look at, and the kind of experiments you could do. Suppose we wanted to go beyond that. Suppose we wanted to simulate quantum cosmology. We actually don't know how to do that. We don't know how to quantum simulate, you know, our own universe, which is an interesting open question in sort of basic science. But we can try to realize versions of cosmology in ADS-CFT. This is work that I did with Sean, Moshe, Mark, Chris, and David, and then also my student Stefano a little bit later, in which we're trying to realize a version of braneworld cosmology in ADS-CFT. So what's the idea? This is, I want to emphasize, you know, braneworld cosmology is an old story, as I'm sure you all know. And of course, people have thought about it in the context of ADS-CFT a lot. Our contribution is to say that for certain particular well-defined microstates of the theory, precise quantum states that you can prepare by Euclidean path integral, you could actually have a braneworld cosmology setup where gravity localizes to the brain, and as in the Randall-Sundrum kind of context, but with the twist that it's behind the horizon of a black hole. So in the usual braneworld story, you'd think about being on the left here, you'd have some, if you talk to Raman, he would say, okay, let's take a cutoff CFT, let's couple it to gravity, and that should be described by some kind of brane, that's this red line moving through ADS. What we're going to do instead is say, well, this brane moving through ADS is actually secretly described as a pure state of some CFT on the right, such that the brane is moving behind the horizon of some black hole geometry that's describing this pure state on the right. Okay. It's something called a boundary state. It's indicating a conformally invariant boundary condition on the path integral, evolved in imaginary time for some amount of time. And so this is a precise Euclidean state you can prepare in the CFT. And the claim is that when you apply the rules of boundary conformal field theory, ADS duality, rules that we more or less know, at least to first order, that this state will exactly reproduce this kind of brane moving behind the horizon. And if we can have the right kind of theory tuned to the right situation, we might be able to make this brane move in such a way that it looks approximately cosmological with some gravity localized on it for a long period of its trajectory. And so then we'd have a precise quantum state we could in principle build in the lab over here. And somewhere buried inside that quantum state is effectively a cosmological dynamics. Very briefly, here's how it works. This slide is just reminding you that there's some known rules for how to describe conformal field theories with boundary conditions in terms of ADS. Basically, the new thing is we need to have an end-of-the-world brane here called Q, such that the CFT space terminates at some boundary, and the end-of-the-world brane starts there and then dips into the bulk, and the bulk terminates on the end-of-the-world brane. Okay. And in the simplest model of this, the brane is a constant tension brane, and it has an action as written down here. So don't worry about the details, but it's just a constant tension brane, end-of-the-world brane. And so you have some equations of motion in the bulk, and then you terminate these with a boundary condition at the brane. For our case, where we're going to have a CFT evolved in Euclidean time with boundary conditions, it turns out there's two possible situations. So the outer region here is the CFT, the edge of your cylinder. And you can think of this length as tau naught and another tau naught. And this purple thing is the brane. So there's sort of two possibilities. The brane can connect in the bulk, in which case that would be a black hole, and the brane can be disconnected in that case it'd just be ADS. These two branes here, this is from the bra, if you like, and this is from the ket when we're computing the norm of this quantum state. So the brane from the future and the brane from the past can either meet or stay disconnected, and that corresponds to the two distinct phases. And it's this first phase that we want to have realized to be dominant in the path integral in order to have the black hole and the brane behind it. This is a Euclidean picture. If I look at my boundary again, now I'm suppressing space, I'm just looking at time. I have my tau naught and tau naught. So this is the Euclidean part of the boundary, CFT. The red is the brane. Here's my Euclidean disk. This is the black hole center point, and this is the brane trajectory in Euclidean. This is what it looks like at a fixed time slice at tau equals 0 here. And so then we can take this initial data and continue it to real time, and that would then evolve forward in real time with our brane behind the horizon of the right CFT. And it would do as I indicated in this picture. It'll expand for a while and then contract and eventually collapse into the singularity. So it's a big bang, big crunch cosmology, where for a large part of the lifetime of the brane, it could look like, say, 4-dimensional cosmology coupled weakly to a 5-dimensional bulk. So the key question is, can we arrange for this so that you have actually gravity localization on the brane? The brane can look 4-dimensional, because otherwise it's nothing like our universe, because we don't easily see ourselves moving in a higher dimensional bulk geometry. It doesn't localize perfectly, but you can write down some conditions, in which case you can analyze the localization problem in some kind of quasi-adiabatic approximation. You would need, for example, the brane to be much bigger than the black hole, and you need the Hubble radius, the Hubble constant on the brane, to be small compared to the inverse ADS radius, some conditions. So we can go back to our brane setup and try to see if those conditions can be met. It turns out that for the simple constant tension brane, we could not find a way to do it. But with Stefano, we were able to, by modifying this thing, slightly adding charge to the black hole, we found that you could approach the necessary limit, the tension 1 limit, by tuning the black hole near extremality. And then in this case, what we found is that you can push the black hole far enough away. I mean, you can push the brane far enough away from the horizon so that for a significant portion of its trajectory here, this blue shaded region, gravity is approximately localized on the brane, and you have some non-trivial cosmology with this relationship between the Hubble parameter and the charges and parameters of the black hole. You have this funny cosmology on that brane and fluctuations of gravity on the same dimension. So this really is a CFT perturbed by chemical potential, where you seem to have a precise microstate that has in its description cosmology somewhere. Let me skip this in the interest of time. There's just some numbers showing that we can get a nice separation between the oscillation and decay of gravitons on the brane, et cetera, et cetera. Instead, I'll just wrap up here. So what did I tell you? I hope the takeaway is that you see that quantum gravity in the lab is a rich subject, and it's not just about trying to detect gravitons. I mean, that's certainly part of it, I would say, but it's a very hard part. And in particular, we can imagine these sort of simulations of holographic models as a relatively near-term goal, where we could still actually learn quite a bit about at least some models of quantum gravity. Questions you can't answer any other way, like finite end corrections to entropy, or medium coupling dynamics, or whether this system is holographic or not, without relying on your standard tools. And this holographic simulation is nice because it also synergizes with a broader effort to understand these complex, chaotic, entangled systems. And maybe the final point is that there's really a lot of open directions. I gave you a flavor of different kinds of things you could think about, how to do simulations efficiently. That brings in interesting questions of quantum simulation, etc. You can ask, how do I detect holography? How do I characterize it from the boundary point of view? You can even ask, what about string theory, this kind of stuff. So there's a lot of directions. And as I said, it's early days in this program, and I think exciting. And I hope if you're interested that you get involved. So thanks for your attention. Sorry for going over a little bit. Happy to take your questions.
Thank you, Ryan, for a very, very clear talk. And do we have questions? There were already a few questions. David, you seem to have
Matthias, can I ask you? Yes.
Yeah, absolutely.
Hello, Brian.
Hello.
Thanks for the talk.
Thanks.
Thank you very much. My question is about one of the slides in the beginning of the first part, where you constructed the dual picture for the traversable wormhole.
This one or a different one?
No. Yes, here. Okay. My question is, we know in the gravity side, in order to render the wormhole traversable, this negative energy pumped into the bulk violates the null energy condition. Then I would like to know what would happen in the circuit side, as something is going to be violated there in order to recover the sign-in state, or?
Yeah, good. So in this side, what's the way to think about that in circuit language is, if you have the thermal field double and you act on only one side of it, you typically raise the energy. This is because it's a thermal state and it already has the minimum energy it can have for a given entropy. And so if you act on any unitary, you're just going to raise the energy, or at best keep it the same. So what you're relying on here is the fact that the two sides are correlated in a specific way, so that if you act on both sides in a definite correlated way, then you can actually lower the energy of the whole thing, but you're relying on that correlation. So there is a circuit analog of the negative energy, which is essentially using the correlation between the two sides to lower the energy a little bit. And in the holographic regime of this experiment, that is the boundary avatar of the negative energy in the bulk. But more generally, in other situations, like this high temperature regime at very late time, this is actually not really the right picture. You don't actually insert negative energy. The energy is already not infinite, but I guess at the middle of the spectrum, because it's a bounded spectrum system. And so you're actually not changing the energy at all, but nevertheless, you can still send one bit. So this is only a picture in a certain regime where it's accurate. And in that regime, there is a manifestation of negative energy in the circuit side. But the circuit itself is more general and can function in other regimes for different reasons.
Yes. Okay. Thank you very much. Thank you.
Any other questions?
I have a question. So when you engineer the cosmology, you put it behind the horizon, so it's going to be difficult to know that you engineered correctly.
Yes. Yeah, I mean, I didn't do it on purpose. I would love for it to not be behind the horizon if I could, but I don't know how to do that. Yeah, so it will be actually hard to probe this, or potentially hard to probe it. In our first paper, we talked about we showed how complexity and entropy could tell you about the brane position, but those are also hard to measure in a quantum simulator. So we need to think about other ways of accessing this. You know, you can look, for example, like depending on what this initial state is, you can apply a certain special Hamiltonian, which actually can send information from the inside back out. So kind of like this teleportation experiment, but now we're emitting information from the brane back out to the right. This kind of setup can be done. So there's a lot to think about in terms of what observables can actually probe the brane physics, and that's just a major open question, I would say. Yeah, you know, and you know, the other side of it is just thinking about how you do this in principle is still nice. Like you can ask, you know, what's the state of the quantum fields on this brane? How does that differ from like the states that we normally consider in cosmology? Is it giving us a clue about how to solve cosmological constant problem or how to think about it in some way? You know, there are a lot of questions we can answer, even if we don't literally go out and simulate this on a quantum computer tomorrow.
Mm-hmm.
Thanks for the questions. Any more questions? We're a little bit over time, as Brian said. So if nobody has an urgent question, then let's just finish the official part, end the recording, and for now, thank Brian again.
Thank you all.
Thank you very much.